But, you know, numerically speaking, that ain't a problem. Okay? No problem. So to address ionized atmosphere, we use this set of equation. Okay, when you do that, look what happens. I warned you, but the physics are a lot different. On the left is neutral fluid, or very, very weakly magnetized fluid. It's for our Jupiter case. You're looking at the potential vorticity from pole down again, and you again see alternating tight, relaxed gradients of vorticity. So you know we have zonal wind. There you are. Okay? But if you turn up the magnetic field in the fluid, look what happens. The gradients go away. The gradients go away. You get no jet. And although I skipped that slide, the reason is, in the slide that I skipped, the reason is the mechanism by which neutral fluids create jet stream is by something, some mechanism that's very well understood and known in two-dimensional turbulence, rotating turbulence. And that mechanism occurs because it has certain conservation properties. One of them is vorticity conservation, and the other is energy conservation. You throw a magnetic field in there, you can see it from the equation. Those extra terms mug that up. So those quantities are no longer conserved, and therefore you can't create the jet. Okay? Very, very different weather system than those. In fact, here's because again, computer, you know, you can do lots of what if experiments. So what you're seeing is top row is vorticity, bottom row is current. Okay, or if you want, you can think of it as magnetic field. The numbers up at the top are called plasma beta numbers. It's fancy sounding, but all you have to know is large number means it's neutral fluid. Very small number means it's really highly magnetized fluid. Okay, so you just do a different set of different runs. When it's very neutral, you get Jupiter back. Okay, you get lots of bands. Great. You start ratcheting down that important beta parameter, and you know, band starts with a little bit fuzzy, but they're still there. All of a sudden, it makes a very sudden transition when the beta parameter is low enough. Okay, then it's a completely different ballgame. In this situation, I know many of you will have heard in weakly magnetized fluid, there's this dictum or saying that the magnetic field follows the fluid. In other words, it acts like it's frozen into the fluid. Okay? But that's only true when the ionization or magnetization is small. When it's strong, it's actually the other way around. The fluid follows the magnetic field. Okay? It's this thing on the bottom row that's like moving the fluid along with it. Okay, very, very different kind of fluid. And in fact, if the magnetic field is strong enough, what you get is sort of like a honeycomb-like structure of magnetic vortices that cover the entire planet. Okay? Very interesting. And these vortices are incredibly strong. You can go in there and perturb it, it doesn't do anything. Okay? You try to knock it down and restart, it comes right back. Okay? Very, very robust. Why is that? And that's the last slide I'm going to show before I close. Remember, these are plasma beta numbers. High meant is kind of neutral-ish fluid. Low meant is very highly magnetized fluid. And we just do a simple experiment where we put down a vortex. Okay? This vortex is really, really simple. It has two patches of constant vorticity. One circle and then an annulus around it. Okay? It's the dumbest model you can create for a cyclone, for example. Well, I guess you could have one patch, but that's really, really dumb. Okay. If you do that, so Q is vorticity, J is the current. It rarely breaks down, and here's the reason why. Okay. On the edges of the angle, the outer ring, when you perturb a vortex like that, there's a wave that skirts across around the edges. Okay, very, very well-known phenomenon in fluids. If you're sitting on the middle in the annulus, and you look toward the center, the waves are going one way. Of course, behind you, the waves are going the other way, right? So we call that a counter-propagating eddy wave. Or if you're a polar vortex, we call it counter-propagating Rossby waves or planetary waves. Problem is, these guys are going at the roughly same speed. So if those two waves are close enough together, in other words, the edge is very sharp, they feel each other, and they get phase locked. Okay? When you phase lock, the amplitude increases, and boom, you lose the coherence of the vortex. Okay? Very well-known, well-studied mechanism. What's going on here? Well, you know, there is a fluid neutral component in the magnetized fluid, so it does a little bit of that too. However, when you have the magnetic field also circling the vortex, because it's a magnetic vortex, there's a new wave called a Fane wave. And these are magnetic waves that go around just like the edge waves, but now this is a magnetic wave that goes around. Now these guys are very, very fast compared to the normal edge waves. So what happens is, even though there are counter-propagating waves, one is going so fast, they never get a chance to phase lock. Okay? It's the old adage, it's so fast, it's not there. Okay? So that's the secret of why these guys are so stable. Right? There's no perturbation. It doesn't suffer any perturbation. All right. So I hope I gave you flavor a little bit for not only the exoplanets in general, but also what makes studying them, at least from a fluid dynamics point of view, pretty fun, pretty interesting. Okay. There are lots of things that I didn't have time to mention. It'd take many more lectures than 1 hour. But there's some obvious things we can do, and that we are doing actually. For example, in fact, many of this we've already completed. So we have a better idea of where the transition from neutral to ionized atmospheric layer are on hot Jupiters. So we've computed that, and it turns out, surprisingly, if you take account of alkalides, so potassium, calcium, sodium, which are known to exist on those planets, it turns out the ionization layer can come all the way down to something like 1 millibar, or a tenth of a millibar. So that's actually pretty far down. It's not surprising if you really think about it, given that it's getting blasted by 10,000 times the normal amount of UV radiation. Okay. Some of that, I just really showed you a very, very simple model. I haven't included things like external magnetic field, the dipole field. For example, very tender Jupiter has it. Venus doesn't seem to be lost it. Mars has it, of course. These guys, does it have it? You gotta do more study. But if it does exist, that brings whole sorts of other sources of perturbation to the atmosphere, namely proton and high energy ions that precipitates down along the dipole field. So that's really hard to include. We're trying to figure out how to include that sort of things. And of course, if it's tightly locked, then you have to take into account that only half of the atmosphere is heavily ionized, the other part isn't, so you have to worry about mixing and so forth. So that's being studied right now. We still don't understand, even in the neutral fluid, example, Jupiter has what we call a super rotating or eastward rotating jet stream at the equator. Do these guys, many current simulations seem to suggest that, but we're not sure how robust that is. In fact, some of our artwork is showing that it's actually more of an artifact of the numerics. You see, exoplanet people generally take models that are designed and tuned for the Earth, and they change the tuning, and they hope things will be okay. And that's a first good cut at the problem. However, it's good that we have our solar system planets to give us some sense, right? So we don't just go hog wild. We don't know how to set these simulations up. So it's good that we have some controls. But what we're learning more and more each day is that solar system planets, they're really different. They're really different, okay? I didn't talk about coupling to the convection, the interior convection region, especially on Jupiter-like planets. Maybe for some other time. And the last thing there as well. And I just want to give you the flavor for how exciting this relatively young field is. It's really cool. You can do both. You can do real planets. You can do exoplanets. I mean, not that they're not real. They'll become more and more real. In fact, there's a mission on the table, as you heard from Boris, at ESA, and also on the US side, to put a dedicated space-based telescope, which will not just try and detect as many planets as possible. We already have 1,000 of them, But its mission is really to just pick, a couple of dozen, and stay on the planet for a long time, so that you can actually do science with it. That's coming very soon, and it's got a very good chance of getting funded and take off. Maybe for some of the grad students here, there's something to think about if you are interested in that sort of stuff. And as I say, it's really fun because it allows you to kind of broaden and be creative in the kind of things you think about. And so I end with this. Picture like this, you go, is it only really limited to the realm of science fiction? And actually it isn't. Because if you think about it, we know from astronomy that actually 2/3 of the star system is binary, the trinary system. Again, we're kind of augmented, solar system's augmented now. The binary star system contains both types of planets. A planet that goes around one star in between the two stars, or a planet that goes around both stars, just like this one is doing. And they both have really, really interesting effect on the dynamics of the weather and climate of the planet. So that's a kind of